Fluid review. So one, density, Zo, it's equal to mass divided by volume. So this is density. The unit is kg, meter cube. And this is mass, and that's volume. So unit is meter cube. Okay, so the important one is the Zo of water is equal to about 1,000 kg meter cube. Okay, so number two, specific gravity. So S is equal to Zo of the material divided by Zo of the water. So there's no unit here. Unit cancel out. So that's specific gravity. In Chinese, this is called 比重. I'm gonna write that here. Okay. And fluid, of course, is called 流体. And this one here is called 密度. Okay. All right. Number three, I'm going to define pressure. So pressure is equal to force divided by area. So the unit is going to be Newton divided by meter square. And there's some other units that we're going to introduce here. So number four, 1 atm, meaning atmospheric pressure, 大气压. I'm going to write that, 大气压. It's equal to 10 to the 5, it's approximately Newton per meter square. So this is also can be written as 10 to the 5 Pascal, PA. PA means Pascal. Pascal. You can also write this as 10 to the 5, just PA itself. Also commonly used, it also can be written as 10 to the 2 kPa. So K here is kilo, and kilo is 10 to the 3. Okay, so that's number four. And then number five, I'm going to continue on this page right here. Number five is the pressure inside a lake, a container. Just when you have a fluid and you know the Zo, and you know the gravitational acceleration is G, then from this pressure right there, from the surface, H, and that's the surface of the liquid surface. So this relative pressure increase, right? That pressure increase, P, at this location is equal to Zo GH, right? So this is not absolute. This is just more than here, right? More than here. That's the amount, that's more than there. So Zo GH, and again, this unit here is kg meter cube. And I'm going to do a little bit of the unit right here. So this is the meter per second square, and this is meter, right? You can see you can cancel them out. So if you do this, then we only meter left. And now you have kg. So then this one here would be kg meter per second square, which is basically m times a. So that is your F. which is Newton, right? And then you have, so you add another meter, so that will be a meter squared down there, right? So then you can see this will still lead you back to the Newton per meter square. Okay, just want to verify this unit for you. Indeed, this P is the unit of Pascal or Newton per meter square. And this is the SI units for pressure, SI units. Okay, so we did ZO GH for 5. And so this is called the relative pressure. Relative pressure. 相对压力. Okay. And let's go to the gauge pressure. Okay, I'm going to do gauge pressure now. So gauge pressure, it's, in this case here, it's similar here. So P is the absolute pressure, which is equal to P0, which is atmospheric pressure, and then plus the gauge pressure. So we're going to call G, gauge pressure. So right here, let's say this is P0, and this is the notation for the atmospheric pressure. This is P0 right there. And so right here, the absolute pressure, if you're interested in the absolute pressure right there, this P right here, so would be the P0 plus this ZO GH. So that would be, so let me just be clear here. So this P is equal to absolute pressure, absolute 绝对压力, right? Will be equal to the P0, which is the atmospheric pressure, 大气压, plus you increase the height, so that's ZO GH, ZO GH. So that's your, this one here is your gauge pressure. That's your PG right there. So the relative pressure and gauge pressure in this case, they are identical. So that's 6. And then we're going to talk about the, so let me clear this. I'm going to talk about some device. So number 7. So this is manometer. This is called 气压计. So it measures pressure for some gas inside a container. Like for example, like a tire pressure, right? So this is like the measure, for example, measure tire pressure, right? Like the tire pressure. So those are the manometer. Okay, so this manometer, you can use to measure the P. So let's say I'll draw this here. So you'll be like that. And then you have the pressure right there. This is your P. And let's say you have a container right there. And that could be your tire. And then you have the water or some other liquid. Okay. And then you have the height difference right there. So right there. So here to here. Okay. And that's right there. And let's say this is the height is delta H. So then this P will be equal to the P0 plus ZO G, the delta H. And the liquid's density is ZO. So that's the pressure that you are measuring. So if you know the height here and you add the P0, it will be getting the pressure of the, so this is the some kind of gas, for example. So in the tire, this will be air. Okay. Number 8, barometer. Yeah, 大气压计, right? Barometer. Barometer. This is used to measure the atmospheric pressure. 大气压计. Okay. So the way it look is like this. So you have vacuum on the top. Okay. And then you have usually you have mercury inside here. This is mercury, Hg. Hg is called gong, right? Yeah. Or called 水银, right? 水银. Mercury, right? It's also called mercury. Okay, and it's poisonous, so you don't want to get too close. So then the height here that you have, right? This is so-called the ZO GH here. So this is the absolute. So this is the P0 that you're measuring here. So this P0 will be equal to ZO G. You want to call that one here H, right? So H. That would be your. So this is your atmospheric pressure, ATM, right? Okay, so that also has some other units. So like P0, you can express that as, say, for example, 76, right? 76. I think 76 is in terms of cm, centimeter, hg. So 公分, right? That one is centimeter, hg. All, so that's equal to 1 atm, right? So 1 atm, if it's just like perfect, and this would be 760 millimeter hg. Okay, yeah, and that would also, of course, be equal to 1 times 10 to the 5 Pascal, and that's also equal to 10 to the 5 Newton per meter square, and this is roughly right there, right? Okay, so that's the that one, and then that's the barometer, and number 9 is buoyancy, Buoyancy, 浮力. Okay, so this one's called 浮力. Okay, and so buoyancy, it's using B, which is equal to, right? Buoyancy is equal to the weight, right? The weight of displaced fluid. So what does that mean? Right, it means the following, right? Say, for example, your water is up to the top, right? And then you put something here, right, for the overflow, right? 溢出来的, right? Overflow. So overflow. Okay. And now you put a rock inside, okay? Then you know the rock, this is a rock, for example. And then once you put it in, you see some water down here, right? So this is some water gets out, right? Okay. And so this is your displaced fluid. 就是被挤出来的流体, right? Displaced fluid. Okay, so the weight of this, so how do you calculate that? You get the volume of this one, right? The volume of your rock. Okay, and then you will get the weight of displaced fluid, right? Displaced fluid, right there. This is fluid, okay? So then the ZO will be the ZO of, let's say this is the water here. Inside this is the water. So it will be ZO of water, right? So then that would be, and then times the G, right? The G of the gravitational acceleration. So then this one here will give you the B that's exerted on the rock right now. This is the B on the rock. And right now you also have mg, right? So we are doing, Newton's first law right here. So that's, you have mg there, and then you also have the normal force, right? So you also have the normal force. So they should be in balance right now, right? Mg should be a little larger, right? A little larger, sorry. This is just mg, okay? Mg, so then according to Newton's first law, you have mg is equal to n plus b here, and this is Newton's first law, right? And there's no net force, right? So your summation F is equal to 0 right now. Okay, so that's that is the Archimedes principle also, right? So it's also called Archimedes principle, right? Archimedes principle, which in Chinese says Archimedes, right? I think that's the goldsmith's his name, Archimedes, right? Archimedes 原理. Okay, so we're gonna continue, and now we're gonna talk about the fluid. Okay, we're gonna talk about the fluid. Number 10. Number 10. We're gonna talk about mass flow rate. Okay, so mass flow rate. So mass flow rate is delta M, right? So just a segment of mass and then delta T, right? So if you have a pipe, so now it's fluid dynamics, right? This is using in the fluid dynamics. Fluid dynamics. So this is in Chinese, it's 流体动力学. Okay, and so this is the delta M, and it flows through this area in the time of delta T. So that's called mass flow rate right here. And the unit obviously is equal to kg divided by second. So that's mass flow rate. And number 12, we're going to say volume flow rate. Right, volume flow rate. So volume flow rate, it's going to be delta V delta T. Right? So it's how much volume. So instead of mass, are we saying, well, how much volume is it, like right here, right? So this volume will be equal to A times this length right there, right? Right there. So that's called this one here, say a little L, right? And this is called the area, cross-section area. This is the cross-section area. So A times L is your delta V right now, right? So this is your volume flow rate, which is meter cube per second. And number 13, we're going to talk about equation of continuity. So 连续方程. In Chinese, it's 连续. This word is 连续, right? 连续, meaning it keep going, right? 连续方程, right? Okay. Yeah, equation means function, right? So this one here, if your ZO is incompressible, 就不可压缩的, right? In Chinese, it's 不可压缩的, incompressible, meaning ZO is constant, right? Same thing. So then this one here will be A1, V1, the equation of continuity, equal to A2, V2. And what are they? So let's say if you have something and your cross-section is changing, for example, but your height is the same, right? Right here, you have A1, right? A1 in this area, okay? And this fluid is moving with a velocity V1. And later, this fluid will be here now, and then your velocity V2 now, and your cross-section is A2 now, it's bigger, right? So this is saying that this has to be the same to basically, this is coming from the conservation of mass. The idea coming from conservation of mass. Okay, but when your ZO is incompressible, then this one here basically it's directly from flow rate. Volume flow rate is constant. This is from delta V, delta T is equal to constant. Okay, originally conservation of mass is saying that delta M, delta T is constant. Okay, yeah, and then when your ZO is incompressible, then you will reach out to that. So this one here, originally this one here will be ZO1, A1, V1 is equal to ZO2, A2, V2. Yeah, if you're using delta M, delta T to the right, you will reach this here. Okay, so we're gonna stop there. And so we're gonna not stop there. So number 13. Number 13, we're gonna say the Bernoulli equation. Okay. Bernoulli equation. So this one in Chinese says 白努力. Okay, means you work very hard, but you get nothing. It's called 白努力. Okay, but that's not what Bernoulli got. Bernoulli actually worked very hard, and you also get something out of it. So this one here says ZO GH, right, plus, well, I guess a lot of people are using Y, so we're going to use Y there. 1/2 ZO V square, and then plus P. So this one here based on conservation of energy. So continuity is based on conservation of mass, but this one is based on conservation of energy. Or sometimes, right, maybe more specific, it's a work energy principle here. And we're not going to derive it, but we're going to review this with you, okay? So this is equal to P, and that's equal to constant. This is called Buoyancy equation, okay? And so what that means is if you have a pipe and you go from one location to another location, and let's say that the y difference, right, in the height, like that, okay? And then the pressure here, let's say, is P1, okay? And then, so then right here, you have pressure here is P2. So then you will then write this one here instead of that. You have Zo, and let's say Zo is constant. Assume Zo is constant, which is usually assumed in our introductory AP Physics 2 class. So Zo is constant, so incompressible, 不可压缩的 in Chinese, 不可压缩的, 不可压缩的. So Zo Gy 1, yeah, plus 1/2 Zo V1 squared. So you have V1, right? So this pressure is by the rest of this fluid here and pushing on this portion right there, okay? This pressure is due to here. And you have V1 is the fluid, the velocity right there, and then plus P1, okay? And the Y1 is here, right? This Y1, let's say if you want to get a reference like that, you can say this is Y1. And you can say, instead of that, you can say then this is Y2, okay? So then this is equal to Zo G Y2 plus 1/2 Zo V2 squared plus P2, okay? And this term is coming from the potential energy per volume. This one here comes from kinetic energy per volume. And this one here comes from the work done per volume, okay? That's the work energy principle. And finally, the last one, okay, number 14, okay, is the Torricelli theorem. So number 14, Torricelli, T-O-R-R-I, sorry, R-R-I. So it's an Italian name. They like to end with the I. Torricelli, C-E-L-L-I, right? Like Bertucci, right? Bertucci also ended with an I, okay? Yeah, so a lot of Italian will end with that. Torricelli theorem, which is a special case of Bernoulli, double L with an I, so that's Italian, Bernoulli, okay? Italian with an I. So this one here says that if I have a water with a big surface area right there, A, which is very big, and then I have a little tiny faucet right there, and then so I have an A2 right there, which is much smaller than A1. And then the height here is Y2, okay? And the height here, oh, sorry, I should say Y here, this one here, let's say the reference is down there, for example. This is my Y2, and this is my Y1, okay? Sorry, not this one here. And then we can then apply this location to that location, and we can say, according to Buoyancy equation, we have 1/2 Zo, and then we have V1 squared, right? So your velocity that's going like that, V1, okay? And that V1 would turn out to be 0 plus Zo G. Okay, actually, we're going to do the opposite, okay? We're going to call this one here 2, okay? Because that's Y2 there. We're going to call this one here 1, okay? 1, and this is 2. So 2 will be larger than 1, okay? Yeah. So then this is Y1. This one is called Y1, yeah. So this is the velocity that's coming out, V1. And obviously, V1 is not going to be 0, but V2 will be. V2 is equal to 0 because this is so much wider than this one here. So it will be very negligible, right? Negligible. Obviously, it's not zero, but it's negligible. So that plus that, and then plus the pressure, which is P0. But P0 will be canceled out because we have P0 here. We got P0 outside, right? So this location here is 1, and this location here is 2, right? So 2 is here, and 1 is here, right? 1 is here, right there. That's your 1. So we apply that to that. So both are P1, right? So here will be P1, but that is P0, which is equal to 1/2 ZO V2 squared, which is 0, right? Because it's very, very big area here, according to continuity equation. So then this is plus ZO G Y2, right? OG Y2 right there. And that's plus P0, right? So P0 cancel out. So now we leave with that. So now we have this right here. So we're kind of deriving again right there, right? So we have, you would go ahead and cancel out all the ZO right there. Cancel out all the ZO. You can now solve for the V1. V1 is then equal to the speed that's coming out, right? The speed that's coming out from this faucet right there. It's equal to square root. And then 2G and Y2 minus Y1. So this is identical to the, when you have a ball and you drop this Y2 minus Y1, right, to this location. And what will be the speed there? What's the speed there? You'll be getting the same equation. So this equation, right, it's the Torricelli principle, Torricelli theorem. All right, so that's it for the fluid review. And keep watching and subscribe, 订阅, okay? And bye-bye.